Well, it is with mixed feelings that I introduced the last lecture of this series. Arthur told me that he's going to miss this engaging audience. He doesn't know what to do with his Saturday mornings moving forward. He'll probably miss you as much as you miss the candies from his wife. But if you are a student from Northwestern, this doesn't have to be your last exposure to networks, because in the spring, I'll be teaching this course. It is for graduate students in physics, math, and engineering, and some of our best undergrads, such as those from physics and the ISP, who are interested in networks and have had some experience with programming and have heard something about statistical physics and nonlinear dynamics. If you're interested in discussing that, just approach me after this event. Now, if you don't have those prerequisites, don't worry. You can still attend the DanceWorks 2024, which just happens to be on the theme emergence. It goes from March 8 through 10, Fridays, Saturdays, and Sundays. It is right here in the Art Circle Drive. And one of the pieces that I'm looking forward to see is this one. In a confluence of coincidences, the choreographer just happens to have my initials and last name. So the inspiration for this piece is crown shyness, is a phenomenon through which trees avoid each other on the top. That is visible. You can see this in photos. What you might not see is that underground, they are connecting with each other through networks of fungi. So in a sense, trees are not very different from people. They behave differently when they are not being watched. And that then brings me to today's lecture, which is on the past, present, and future of technologies that are enabled by research in science and engineering in the area of networks. So the first thing you should think about then is what a technology is. I'm sure Arthur will define that. I will define what people think a technology is. A very famous computer scientist, Alan Kay, once said that technology is something that was invented after you are born. Reason why no one regards the wheel as a technology, and very few people regard a pen like this as a piece of technology. But before we get to that, I want to thank the people that have been involved in this series, starting with Paul Sievert, his family, for the support, not just financial support, but other forms of support that have oriented the lectures over the past 3 years since it was initiated. It's more than 3 years. That was a good one. And I should mention that next year, around the same time, there will be a new series on a new topic. So you should already mark your calendars for that. Many thanks to the current and previous chair of the physics department, André de Gouveia, and Mark Schmitz for respectively running it now and in the past. The many staff members from the department that have been involved, and especially Vaso, Jason, Ellie, and also those that are here right now helping with Zoom and other technologies that we need. Many thanks to Camila. It was a big enhancement to the lectures to have something to look forward to in addition to the lectures themselves. Thanks to Jory. And today I heard we'll have a very special guest, Charlotte, a student from the department who have cameo in this lecture. So I'll thank her in advance for being here. And of course, many thanks to Arthur himself. He'll be lecture deprived after this, so you guys should be encouraged to reach out to him to discuss your ideas about this area and ask questions and perhaps propose solutions to problems. Arthur will be around for a few more years. And well, that's where I would leave things. So thank you very much, everyone, and thank you, Arthur, then for these inspiring lectures.
Thanks. Thank you, Joseph, for the introduction. So let's start with the definition of the meaning of a technology. So a technology is an application of a knowledge that solves a practical problem. So when I just mentioned a pen, it solves the problem of writing or recording information. The chairs that you're sitting are also a technology on itself. Some chairs are more technological than others. Some seek to maximize comfort, others ergonomy, and so on. The difference is that an idea or a theory is not a technology, not until you put it in practice. So it may be the path towards a technology, but it's only a technology when you actually can get a concrete solution out of that. So they say that in order for us to see the future, we have to first understand the past. So I'd like to start this talk on the creation of infrastructure networks, many that we already have available in the current day. Take the power grid, for example. Right now, we have 12,000 power generation facilities in our power grid, supplying over 1 million megawatts of energy. And that's being distributed on 200,000 miles of high voltage lines and over 5 million miles of local distribution lines within our cities. Now, how did we get to this point today? Well, it always started very simple with a highly local power distribution center. That's the Pearl Street Station by Thomas Edison in the south of New York. It was supplying 100 kilowatts of energy only, and that was being distributed to 400 lamps to 82 consumers. Now, notice how limited it was in scope. This power plant was supplying energy only to the blocks that were around it. 2 years later, this number of lamps and consumers would increase to 10,000 lamps and 500 consumers, but there would be some bottlenecks on that. Well, that would be because of the insistence of Thomas Edison on a DC design for the power grid. So if we have 1,000 lamps of 60 watts, that's a power demand of 60,000 watts. And because of the DC design, it turns out that the voltage level in which the power was generated was the same voltage level that the power was being transmitted. And because the power was being generated in a high or in a low voltage level, the transmission would also be on a low voltage level. That's 110 volts. So if you do the math, you can calculate those currents, and that would be a current of 500 amps. You would need the cable this thick in order for you to transmit all this power in a single line. And you can imagine that the power losses would be huge. In fact, they increase with the square of the current. So this led us to the famous war of the currents. On one side, we had Thomas Edison and his DC design, but on the other side of the ring, we had George Westinghouse and the AC design. And Westinghouse had 2 cards on his sleeve. Those were the rights for Tesla's AC induction motor, which would be important for the scalability of generation of energy, both from hydroelectric and thermoelectric power plants. But he would also have the rights for the Gallard-Gibbs transformer. And a transformer is an electromagnetic equipment that allows you to elevate or decrease the voltage level during the distribution of your power. So in other words, now we could generate the power on a low voltage level, and during the transmission, we use a transformer to elevate this voltage level to a very high voltage level, for example, 110,000 volts. And because of that, the current would be way smaller. That's 0.6 amps. If we do the math, you would now need a cable this thick in order to transmit this amount of power. And because of that, the power losses would be way less than the one from Thomas Edison's. At the end of the day, we know that Westinghouse won this war of the currents precisely because of the technology that allowed him to minimize power losses. And that would be the same technology that would be used in the hydroelectric power plant in Niagara Falls. In fact, Westinghouse had 9 of the 13 patents that were used to generate power in Niagara Falls. And it was based on this technology that the first AC transmission line was created, linking Niagara Falls to Buffalo over 26 miles with a voltage level of 11,000 volts. The first high-level voltage line would be created later, connecting San Francisco to LA, and that would be on a voltage level of 115,000 watts of volts. By the end of the First World War, the power grid would look like the picture that we have here in the United States. It would be completely disconnected. But past the First World War, demand for power would increase exponentially. We would see demand for lighting applications, industrial power, electrical railways, and so on. And a turning point in this story here was the realization by utility companies that they could profit by interconnecting that electrical systems. In other words, if I have a hydroelectric power plant and you have a thermoelectric power plant, it is beneficial for me to buy your power when my river is running at a lower level, but it's also beneficial for you to buy my power when my river is at a high level and I'm producing more energy than I can actually use in my system. In more technical terms, that the enormous benefits of scale and the enormous costs of competition due to redundancy in the infrastructure led electric power providers to accept state regulation of rates of return in return for monopoly control of regional markets rather than competing among themselves. Well, that led to 1933, where now 70% of houses had access to electricity, 40% of houses had washing machines inside their homes, and we could have a picture of the power grid that it was way more connected than we had before. In fact, these numbers would only keep increasing. By 1936, 30% of houses had refrigerators, and the feds would also realize that there were benefits in the resilience and the decrease of vulnerability in the power grid when we interconnect itself, which would also be useful for the manufacturing processes during the Second World War. So when you look at the creation of the power grid, you can notice 2 underlying features. One is that it happened in a decentralized way. And the second is that new interconnections tended to be attached in a preferential way following the demographics and the natural resources in the area. That would be more or less the same strategy that we would see in the creation of telephone networks, but also, even if we go back in time, to the creation of road networks during the Roman Empire in the south of Europe. In fact, the story of the internet followed the same trends. So it started with the funding from the Advanced Research Project Agency that created a network of computers so that they could exchange data between themselves. And that led to the ARPANET for scientific and military purposes. Well, this computer network was further expanded, connecting the 2 coasts of the United States. And 3 years later, it would also be internationalized with a connection to London. But by this point in time, the agency realized that it would be very hard to keep with the increase of this infrastructure in a centralized way. So they decided to decentralize this computer network. In other words, they created shared protocols. Those would be the TCP and IP protocols that would allow data to be exchanged between different types of computer networks. For example, the phone net, the ARPANET, the X25 net. And this would lead to the creation of the internet. We skip 10 years later, and the internet would be privatized. This would allow telecommunication companies to take the internet to our homes for public usage. And nowadays, we have the internet as a global infrastructure connecting the entire world. In fact, we can see here undersea cables undersea cables connecting optical fibers, which are the fastest way of transmitting data between any two endpoints. And the internet, it would also reach to the skies. The Starlink forms a network or a constellation of 5,000 low orbit satellites that allows the internet to be provided with low latency, even to remote areas around the globe. So when we look at the history of infrastructure networks, one might ask whether the creation of networks is an inevitable process. So let's look, for example, at the S&P 500. So this is an index that tracks the 500 largest companies listed on stock exchange in the United States. And we can ask, what do these companies have in common? Well, first of all, they are rich companies. But second of all, they all depend on network technologies. So for the next slides in this presentation, I would like to cherry pick some examples of the types of different network technologies that those companies are employing today. One that we have already discussed in this series of lectures is the PageRank algorithm that was used by Google for a search mechanism. This was discussed in the third lecture of the series. We already know that the PageRank algorithm is related to random walks on a web graph. A web graph is a network of interconnected websites, and that's also related to the eigenvector of the adjacency matrix that is related to this network. But the important message here is that the network here is not an infrastructure system, is not a physical object. The network technology here is an algorithm. It's an algorithm that allows you to find what are the most relevant web pages in a network of web pages to your search. And many other companies use algorithms that are based on, or technologies that are based on networks. For example, the Netflix recommendation system is also based on a network system. On the one side, we have users. On the other side, we have the content and the movies. And it turns out that if I like The Matrix and you like The Matrix, then chances are, so if I like The Matrix and you like The Matrix, but you also like the Jurassic Park movie, then chances are that I will also like the Jurassic Park movie. So Netflix can recommend that to my feed. We can create those recommendation networks as a bipartite graph. That's a network where we have two layers, one layer of users, one layer of content, the interconnection between them. And we can even expand this recommendation network by including other layers like the type of movies, the directors involved in those movies, your favorite actors, and so on. So that's how Netflix sells you their content. In fact, many of those network technologies and companies depend on a kind of network effect. So that's a positive feedback loop where more users lead to a better service, at least in theory. So word of mouth referrals lead to more new users and active participation in platform, which in turn leads to user feedback and data that can be used to improve value and user engagement. Now, the question is, how do these companies like Facebook incorporate this user feedback and this data in order to improve the value of their platform? So if Facebook were to take a social network of a random person and the friends of this random person, then you would have a network that would like a blob indistinguishable that we have in this slide here. You can barely see the people, you can barely see the connections and who is interacting with who. It's a very large scale system. So how does Facebook make sense of this in order to curate its content? This is a process known as social network analysis. And one way to deal with that is by creating algorithms or technologies that allows it to create or process this data information. For example, the creation of communities. So if I'm a friend of Adilson and Adilson is a friend of André, and André is also my friend, we form a triangle of interactions, and that is a community on itself or a cluster. And we can use those clusters to identify communities, and we can use those communities to create content to people. So we can take Jürgen's social network. If you don't know who Jürgen is, that's not a problem because Jürgen is like the average user of Facebook, a nobody. But even though you don't know who Jürgen is or who his friends are, you can process the network structure of Jürgen and separate it by different communities. And if you further can identify what those communities are related to, for example, his hometown, his friends that he made during his trip to Ethiopia, Canada, then you can use the information of those communities in order to feed content to his webpage. So chances are that Jürgen will be interested on whatever type of news that his friends in his hometown or from his university were looking at. So you can use this information to send to him. On a very different level, we can also see how network technologies can be used to medical applications. So here we have a timeline for the process of drug discovery and development. It's a very long process. It takes more than 10 years. It can cost up to $1 billion because it involves several steps. You have to design a drug. You have to do experiments in cell lines. You have to do experiments in animals like mice. And finally, you get to several stages of clinical trials with humans. And then you do the registration of your drug. Well, there is one way to speed up this process, which is known as drug repurposing. And drug repurposing is when you take a drug that was already successful to treat one disease, and you find another disease that can be treated with the same drug. And because this drug was already approved by the regulation agencies, then you can simply skip most of the initial stages and go directly to the clinical trial phase. One classic example is Viagra, which was originally developed for pulmonary hypertension, but it turns out that it was way more effective and profitable for erectile dysfunction. That's an example of an accidental drug repurposing. They were not looking for this application when they started developing the drug itself. But there are other types of drug discovery that employ techniques that come from the context of network medicine, or that use information from networks in order to find new applications for drugs. One example would be the posaconazole and the revconazole. Those are drugs that were originally developed to treat fungi infection, but that now are in clinical trials to treat a parasite, which is the Chagas disease, a very common disease that we see in tropical areas like Brazil. So how do you use this information? What is the technology going on here? The technology are algorithms that are used to process the information, model the networks, and pretty much do bioinformatics and try to find patterns between the data. So in this case, we have right here on the left an example of a protein-protein interaction network. We have already discussed those types of networks in the context of irreversibility in the previous lecture. But the idea is that we have different nodes. Each node represents a protein, and we create a link between those nodes if a given protein interacts with another protein in order to either produce another protein or inhibit another protein. So if you have prior knowledge of what are the pathways that are associated with what are the pathways of proteins that are associated with a given disease, and what are the pathways associated with another disease, and you can find common pathways between those two diseases, then you can use this information to tell that maybe one drug that was used to treat this first disease might be useful to treat the second disease because they simply share the same pathways. There is a chance for a new discovery here or repurposing. So you can use data science and network methods in order to curate a network of how proteins interact with drugs and how drugs interact with disease and create this very complex network with possible new candidates for drug repurposing. So we go back to this picture, and for all those companies that deal with physical products, there is a very common network among all of them, which it's very important to how they become profitable in itself and how they optimize their gains and costs. And those are the networks based on supply chain distribution networks. It's a concept that goes all the way back to Henry Ford and the Fordism. That was the idea of creating consistent, standardized products for mass production and mass consumption. And it's how nowadays we have full teams of production engineers that are simply optimizing how a product goes all the way from suppliers to customers in optimizing the costs and the gains that come out of this movement of projects. But this is a network that requires optimization on itself. We're going to be seeing how we can optimize this network. But first, it is important for us to realize that several technologies were required in order for us to see those supply chains being applied in an efficient manner, how we see today. For example, that was the movement between products over long distance was only possible due to the consolidation of train and railroads in the 1900s. It turns out that pellets wood, a pile of wood, is an important technology that allows inventory optimization and inventory management. And it was largely applied during the Second World War for distribution of items and equipment. If we move forward in time, now the shipping transportation of goods would only be possible during a process known as containerization, which is due to the fact that in this period of time, we had all the machinery available for us to move large loads and containers to ships and so on. And finally, also in the same strategy of inventory optimization, the barcode would be an important technology that would help keeping track of what were the products that were being used that were being stored in plants and distribution centers. And finally, with the advent of computers, this data could be processed in an efficient manner, and those technologies could be further optimized so that the supply chain could be designed in such a way that goods can be moved through it in an efficient manner. Now, it's important to realize here that networks are really good for one of the specific applications that networks are really good at is for moving goods in a fast way, whether this is for good, like in supply chains, or for bad, like in epidemics. So we can compare the Black Death and the COVID-19, and with only road networks, we would have a spread of the Black Death like a wave over 5 years throughout the Euro-Asia, whereas COVID-19 would take only 2 months to spread to most of the world. So what is the technology or the algorithms that these companies use to optimize network distribution? Let's take the Google Maps as an example. So it turns out that my cats are running out of food. So at some point after this lecture, I'm gonna have to go stop by at PetSmart to get some extra food for them. The question being, if I ask Google Maps, what is the best path that I can take to reach PetSmart? How does it calculate those routes? What is the algorithm being used here? Well, this is based on an algorithm that was developed by Dijkstra in 1956, a computer scientist. And we can represent this road network as a graph or a network of nodes and edges, where each intersection in the road each intersection in a road is represented by a node, and each edge represents a road and its corresponding traveling time. So the Jigsaw algorithm allows you to find what is the most efficient way for you to move from one starting node to one final node. How does it do that? It does it by creating a table. So for example, for you to go from A to A, the distance is 0 itself. But then we can look at the closest nodes to A. So those would be C with a traveling time of 4, node D with a traveling time of 8, and B with a traveling time of 1. And we can fill this table like this. Now we choose the one that has the smallest traveling time connected to A. That is the path from A to B with a traveling time of only 1 minute. And then we see what are the new connections that B has with the rest of the graph. These are D and E. Turns out that it's now faster for you to move to node D by going through A, B, and D than rather than directly from A to D. So we keep iterating, but we always follow the path with the smallest traveling time that was detected so far. So from all of those different paths, AC is 4 minutes, ABD is 3 minutes, and ABE is only 2 minutes. So we follow this path from ABE, we iterate. Now we see that there is a new path to D and H, but the shortest path is now ABD because that's 1 minute plus 2 minutes, 3 minutes. So we keep iterating like this until finally we can find what is the shortest path that connects A to I. That would be this very non-trivial path that we have here, A, B, D, G, F, and I. Well, for this type of strategy or algorithm, this is based on global knowledge of the network structure. And also, it turns out that if the network is very large, then calculating all the possible paths from one node to another node may be very time consuming, right? So we may have to think about strategies to optimize that. And that's what Google does, for example. So if I'm going in a southwest direction, we may do an educated guess that probably I don't have to be moving north or east that much. So we try to incorporate those educated guesses into heuristics through the algorithm, and that leads to the A-star algorithm, which is close to the algorithm that is actually used by Google. So for example, here we can see an animation that shows the smallest path that connects a grid from the top corner to the lower corner, and we can see how this A-star algorithm iterates over time. And you can see that even though there is like some short paths that it could potentially take on these regions, it doesn't, because those heuristics are telling him that most of the time he should be trying to move on the southeast direction instead. This type of algorithm is not really that different from the algorithms that are used for video game characters to move in a space, for example. And we could be talking about how this network routing is used to move people, to move products, but it can also be used to move data. And it's not really that different in the context of data communication and the internet itself. But let's move forward to another example. So going back to this picture, I'm now highlighting in yellow at the top here different companies from semiconductor technologies. Those are NVIDIA, Intel, AMD. So what are the common technologies that they have that also employ networks? Well, let's look at how integrated circuits are composed. We have the Moore's law, which tells us that the number of transistors on a microchip doubles every 2 years. So by 2020, integrated circuits were counting with more than 50 billion transistors. And you can see how this becomes a very complex network on itself. How do we integrate those transistors? If we look from the bottom up, we can see that the transistors are devices that basically work as gates. They either allow a current to pass or not to pass. A transistor is part of a logic gate on itself. That is an example of a NAND logic gate. Basically tells you that if the two inputs are 0, the output is going to be 1. And if the two inputs is 0 and 1, it's also going to be 1. And if the two inputs are 1, then the output is going to be 0. So transistors are part of of the construction of those logic gates. Those logic gates are used to construct logic circuits, which are used to process data in bits. And finally, those logic circuits are part of a very large integrated circuit like this one being shown right here. So how do we design this? This is a method or a technology that is known as VLSI, very large scale integration of networks and circuits. And it's a process that involves several steps on itself. We have system specification, what's the chip is going to be used for, what is the architecture design and the logic design that allows you to achieve this function. How do we implement this in the form of logic circuits that do these logic operations? But finally, we have to make it a concrete object. So we have the physical design that actually implements the circuit in a physical manner. But if you look at a logic circuit from a diagram level, you can see how this process can be very complicated, right? We're just increasing the scale of our system. We now have multiple types of logic gates integrated to each other. So how do we know that they are working as we designed them? When we constructed them, how do we know that the voltage output and the operations that are being done work as we expected from the modeling and from the simulations? Well, that's a hard process on itself. So what engineers do is that they break down this problem into smaller problems. And they want to break it down into smaller problems so that each smaller problem can be studied on independently, but also in such a way that when you plug them together, the intercommunication between those two blocks have the smallest number of interconnections possible. So you minimize time delays and other communication costs. So for example, if you take, so this is a process or an algorithm that is based on graph partitioning. So for example, if you take a logic circuit like this one, we have multiple logic gates interacting each other. And if you were to try to break down the circuit into smaller parts, you could do a naive cut like this vertical line with the cut tool here. And you would arrive on two blocks that have 4 interconnections between them. But it turns out that if you do a more smart cut to partition this circuit into two other types of blocks, you can find a more non-trivial cut like cut 1 that allows you to separate the circuit into 2 blocks that now only have 2 interconnections between them. How do you do that? Well, you can do that by employing algorithms and technologies like the Kernighan-Lin, which are essentially heuristic methods that are developed to minimize the number of interconnections between those partitions. And there are several ways to do that. This is an old-fashioned algorithm, and people are trying to develop more smart strategies to help in the design of integrated circuits, especially because they are getting increasingly more complicated. And one path to do that is by using integrating AI or neural networks in the design of chips. That can be done on several levels. We can use it to design device levels. We can use it to design devices, logic gates, logic circuits, and so on. There are many ways that these neural networks can be employed, and it becomes a kind of positive feedback loop where you are developing AI models to improve the performance of your circuit, and then you can use the circuit in order to improve the performance of your neural network. At least that's how naively we would conceive. Because of that, we have many types of companies investing in neural networks and artificial intelligence. Those include Apple, Google, Amazon, Facebook, Microsoft, being one of the leaders with OpenAI and its recent application with ChatGPT. But neural networks are the kind of talk that we are seeing currently today in every news. So instead of focusing on the role of neural networks in technologies, I would like to have space to other types of technologies, others that people may not have the experience or have not been seen talking about in the past days. One of those technologies have been seeing massive investment from NVIDIA, IBM, Google, Amazon, Honeywell, Microsoft, and so on. And that is based on quantum computing and quantum internet. Now, to do this part of the presentation, we invited the PhD student from our center, that is Charlotte, who's an expert on quantum internet and quantum communication on itself. And she's going to be able to tell us more about this story in precise detail so we can have an overlook of what is the current technology and the future path towards it. So let's welcome Charlotte.
Thanks, Arthur. So quantum internet is a network of quantum computers that is being developed. And it will also allow quantum communication between those computers. There are two main fields in this: quantum network science, which are quantum computer and quantum communication. So when we talk about a quantum computer, you might think it's just a powerful computer, something similar to the classical supercomputer. It can have hundreds of thousands of processors. We have one here at Northwestern for our scientific research. But actually, that's not the case. So quantum computers are very different from the classical ones. It's kind of like comparing a light bulb to a candle. No matter how powerful the candle is, it's not a light bulb. So you might see some photos of quantum computers like this and wonder what's actually inside it. To answer that question, we will start from how classical computers work. So classical computers work with binary digits. So it has zeros and ones. Different from the base 10 we use every day, it uses base 2. So it will turn anything like numbers we use or photos or videos into those binary digit strings with only zeros and ones. And it's very different in quantum case. So a quantum bit, which is called qubit, is actually a superposition of two states. So think of having an electron. It can have a spin up or a spin down, or a superposition of those two states. And when you make a measurement of a qubit, you will end up having either 0 or 1 because the quantum state is being destroyed. And the probability of having those two results depend on your states, which is here defined by alpha and beta. With one qubit, you can have a superposition of 0 and 1. And with two qubit, it will be a superposition of 4 states because you can have 0, 0, 0, 1, 1, 0, and 1, 1. If we compare this to a classical bit, when we have two classical bits, it can either be one of the 4. So if you want to have all the information containing 2 qubits with classical bits, you will need at least 8 bits to do that. And this number will start growing. When you have 3 bits, you will have a superposition of 8 states. And with the classical bits, you will need 24 bits. And it will grow exponentially when you have more and more qubits. For example, if you have 300 qubits, you will need 10 to the 9th, more than 10 to the 90th classical bits. And that number is even larger than the number of total atoms in the observable universe. That is to say, it's not possible to use classical computers to simulate the qubits. It's actually the same in computers. So when you connect two classical computers, the capacity is the summation of those two computers. But it's different in quantum computers. When you connect them in a quantum way, and that they can communicate, they can do quantum communication, then the capacities are actually the product of the capacities of those two computers. And when you have more and more computers to form a quantum computer cluster, the power of it will be very large. So because we have superpositional states in quantum physics, it can make the parallel calculation exponentially faster. I'm not claiming that any problem can be used in quantum computer and it will be super fast, but just for certain types of problems. So that is very powerful. So that is why we need to build quantum computer. And quantum computers are actually networks of qubits. I'm showing different topologies of quantum chips that was built by IBM. So these blue dots here, each of them are a qubit. And the quantum computer can do quantum gates, logic gates on those qubits. For example, if we have a quantum NOT gate operating on the qubit, it will flip the state of that qubit. And you can see qubits that are connected with the string there. So the quantum computer can perform 2-qubit gates on those qubits, like control NOT gate and something else. So there are so many companies that are working on developing quantum computers. And among them, IBM have this development roadmap that they are developing quantum chips. So they started from something very small years ago, like only with 5 qubits. And then last year, they launched the first quantum chip with over 1,000 qubits. You might think that's pretty good. That's maybe the end of quantum computer, but that's not the case, because those qubits they have are not perfect or ideal. They are affected by error and noise, and there is still a long way to go. IBM also built an online platform so that we can log into those quantum computers from our computer and do quantum computing on those computers. So there are many potential applications of quantum computer. We can start from simulating some quantum systems in physics and chemistry. For example, last year, there was a paper published, and the scientists were simulating the electron structure of a particular molecule using the 27 qubits quantum computer from IBM. And that's not possible using classical computer or even supercomputer. And with that, quantum computer will benefit the discovery of drugs and design materials. Quantum computers can also be used for quantum machine learning. That will be much faster than the classical ones. And also there are some algorithms that can benefit from quantum physics. For example, 30 years ago, a mathematician, Peter Shor, developed an algorithm, which is well known today as the Shor's algorithm, that can factorize large numbers using quantum computers. So as you know, the classical cryptography that we use today is relying on the impossibility to factorizing a large number. But with the Shor's algorithm and powerful quantum computing in the future, that will be easy to crack down the key that we use today. The day is not coming, and you might wonder, maybe in the future, I won't have a safe bank account. But actually, that's not the case, because we can use quantum cryptography, and that's even better. To explain that, we might go back to talk about the quantum bit. So we said it's a superposition of 2 bases. And if we have 2 qubits, it can actually be in a special state, which is called the entanglement state. That the quantum states of these 2 qubits are correlated with each other. So we have 2 electrons that have spins, and they're entangled. So when you measure the state of one of them, you get a spin up. And so that you automatically know that the spin of the other one is also up. If the first one is down, then the other one is also down. So since the quantum states of them are correlated with each other, they have special properties. With that, we can do something really fun. That is the entanglement teleportation. This is not the teleportation you saw from Star Trek, that you might be able to teleport a person or an object. But here we are teleporting qubits. So imagine here on the Earth, you have 2 qubits. One of them is in arbitrary state, psi, and then the other qubit is entangled with the qubit on the moon. They're entangled. And then you can do some quantum operations on the 2 qubits you have on the Earth so that they will be entangled. And instead, the state of the qubit you had is now transmitted to the state on the moon. You don't even know what the state of your qubit is, but boom, without any delay, the state is on the moon now. With this, we can do quantum communication by sending entangled photons or particles to a long distance away. And then that can realize quantum communication. And it's very secure from a fundamental physics level that no one can crack it. There are many potential applications of quantum internet, including quantum cryptography that we just talked about. And we can also have a network of quantum sensors that relies on entanglement. We can also privately use quantum computers in the cloud that we can communicate quantumly with those computers so that nobody will going to know what you did on the computer. There's also one prototype quantum network that we had just around us, which is called the Illinois Express Quantum Network. It has 4 locations, one here at Northwestern, one at the downtown campus, and 2 other locations at the national labs. So at these 4 locations, they have devices to create entangled photons. And then they can send those entangled photons through optical fibers that we already built for classical communication. And with those entangled photons at different locations, they can have quantum communication. Professor Pram Kumar at Northwestern is part of this project, who contributed a lot. But the vision of the quantum internet is to allow quantum communication between any 2 locations, but not just from here to Chicago. And to do that, it's actually a problem of distributing entanglement, that quantum computers can send out entangled particles to other locations. But those entanglements are not perfect and ideal. So we need further quantum operations to make those entanglements better so that we can have a quantum internet that can be used. And that's a problem of percolation that is being developed and studied right now. So Professor Eastman Kovacs at Northwestern is also contributing to that. And we look forward to having a quantum internet in the future. That is all my talk. So I will give back this to Alfred.
Charlotte will be available for the Q&A session afterwards, so if you have any quantum questions. So switching from quantum to the control of, well, the quantum computers on itself have different types of processes that require control. We also have problems of control on how we stabilize the flight motion of airplanes or even a single drone. But future technologies require now the control not only of a single process, a single component, or a single drone, but the control of a network of interacting drones. So I want to give a brief overview of the contributions in this field, or the problems in this field, and how this technology may come in the future. But first, let's focus on the problem of controlling a single agent. This is an example of a competition of drone racing that is done on a predefined course. But here the control is being done by a human, right? So it's the human that is defining the velocity, the speed, the turning of this drone, and how fast it can go, up to the limitations of the drone itself. But when we go to autonomous drone control, there is control that requires no human intervention. The problem becomes a little bit more complicated, but it's still a problem that we can solve using old technologies developed in control theory from the 30s to the 60s. The framework here is basically, the idea is that, can you design a drone that automatically stabilizes its flight motion in the center of a room? The answer being yes. You can see that being done by a student inside his dorm. He designed the entire thing in this project back in Cambridge. But the problem can be formulated as a feedback control loop, where you have a system that is the drone, some measurement that you take out of the state of the system. Those would be the position and velocity of the drone. You feed back this information and you compare to the reference input. The reference is the center of the room where you want this drone to be. And you measure the error between the state of the drone and where you want the drone to be. That is going to be the control error. And basically, the larger the error, the larger the gain on the control action to correct this error. So that is a proportional controller. But you also want to integrate this error to 0 over time. So you also use the integral controller. And with that, we have the very classical proportional integral controller that we see in any kind of airplane from the very beginning in the 30s. But the problem becomes way more complicated when we have to deal with multi-agent systems, the example being drone swarms. The reason being because each drone is a small computer on itself, but it has a limited computation and processing capability, right? So each drone can only get access to the state of the drones around it in a limited fashion. It has limited communication channels for the measurement of the state of the other drones. And even if it had the information of all drones around it, it most likely would not have the sufficient computational power to process all this information and use it for the control of its own state. In other words, when we go back to this feedback control loop here, each drone only has information of a limited subset of drones around it. That is a problem that becomes decentralized. And you can see that this drone here only interacts with the drones that are closer to him. So how can you design a feedback control loop that allows you to govern the motion of these drones in an autonomous way and efficient way? That's a technology that has been seeing massive investment by different companies from Amazon to Intel, Microsoft, and Sony. And there is like different potential applications for it. Delivery, mapping unknown terrain, monitoring crop growth, early detection of forest fires, law enforcement, entertainment, and so on. But the problem is really hard, especially when you deal with unknown terrain itself. So if you go outside from your own dormitory and now you go now you design a robot or a drone that can roam the streets, things get way more complicated, and we have examples of some hard challenges that we're seeing with this delivery robot from Uber Eats in Canada. Well, you can see on the very first video that there is a very large obstacle in front of it, and it's paralyzed without knowing what to do, right? I'm sure that they put the cute face on it so that people can help it. And I mean, it can become a dangerous travel as well, right? So, poor guy. Well, that's only with one drone roaming in an unknown terrain, right? If you have now multiple drones, now you have a congestion problem. And how do you make them? How do you design a feedback controller that would allow them to dodge each other and move in an efficient way in this space? Well, the problem is being investigated. It's a current discussion in the research stage so far. But here is an example where you can see drone swarms naturally dodging obstacles on a forest of bamboos. And we can see how they maintain their formation as they move around this space, even though they do not have prior information of the obstacles along their way. Well, those drones are operating on a decentralized way. And the difference between the type of feedback controller that I showed before and these ones is that before it was based on linear control schemes. And here they use something more sophisticated. It's called an MPC, Model Predictive Control, where they're using a nonlinear control scheme to predict the trajectories and try to find control actions that would lead to better trajectories in their path. I could talk about different types of applications in network control in the context of power grids, but since time is short, I want to move to the concluding remarks on this lecture. And well, you know, technology is a relative thing. So what I consider a technology may be very different from what you consider a technology depending on when you were born. So you may not have realized this right now, but I structured this presentation in a timeline where first I presented technologies before I was born. Those were the creation of infrastructure networks, power grid, telephone networks, internet. All of this stuff was already there when I was born. But then during my elementary school to high school times, I got the chance to be interacting with new technologies. Those were the World Wide Web, Google, social networks like Facebook, and more sophisticated integrated circuits and electronic platforms. During university and PhD, we have been seeing current investments in artificial intelligence, Internet of Things, robotics, but the current research in the future remains to be seen on how technologies like quantum internet, network control, network medicine can benefit our environment for practical purposes. On a brief note, I would like to say that network theory is not only about technologies itself, it's also about policy making and helping governments doing decisions. We have been talking about this in the context of different lectures. In the friendship paradox, we talked about how sampling bias can be used to do a more efficient epidemic monitoring. We talked about how we can use modeling to identify system vulnerability to cascades in the power grid, and how current actions in the climate can lead to irreversible changes. I want to highlight this paper on the critical transitions in the Amazon forest system, because it's a paper that was published online on February 14th. That was a Wednesday following our talk on Saturday on irreversibility. So it came right after the talk itself. But it beautifully illustrates the type of transition that we were discussing in the context of a more simple model, showing how a dense forest can transit to a savanna forest state. If anything, this serves as an example on how important it is for us to keep up to date with the literature. And for that, I thank the members of our group, which have been helping us tracking those papers and recommending them for those suggestions. Well, with this, we arrive at the end of those series of talks. We have today, it was about the advent of network technologies with a case study on quantum networks in particular. If I had time, I would like to cover many other types of topics, but that's it for today. We could have been talking about more about network control, network medicine, neural networks, and AI. But I want to perhaps show how we use it this time to discuss the many type of emergent phenomena. Those are phenomena that are more than the sum of the parts that happen only because of networks. Those were synchronization in homogeneous systems, contagion and epidemic spreading, and how it relates to the friendship paradox, flowing networks and its relationship to the Bryce paradox, cascades for the modeling, prediction, and control, multi-stability, which allowed us to talk a bit about bifurcations and dynamical systems, and then back again to synchronization in heterogeneous systems. The Sievert Prize Lecture Series has been going on since 2022. I'd like to thank Paul Sievert for organizing those lectures in memory of Eileen. This gives us a special opportunity for researchers in early career stage to not only prepare these talks, but get the experience to do them. In 2022, the talks were focused on particle physics, then quantum machines, and finally, we see the end of the networks and complex systems. So I'm going to be excited to see what we're going to be having in the next year in 2025. Special thanks to the members of the department, André, and also the various staff members that have been helping in the organization of these lectures and making them available online for the public. Special thanks to the members of our group for the discussions that I have been having on the content of those presentations. Thanks to my supervisor for all the discussions and curating of this content. And with that, we can see a common expression that he has, which is the fastest path to new technologies is to develop interactions between existing ones. That's precisely what we have been seeing in these previous examples. One type of network that I have not commented before is the family itself, which is a supporting network that has been helping me with these preparations. I couldn't choose which cat picture to take, so all of them here. And with that, we're open to Q&A. Thank you very much for staying here with us and taking your time to enjoy these lectures. If you want to have access to the previous recordings, you can use this QR code here to access the previous lectures. Thank you very much. Yes, I'll leave it there. Thank you very much.